Hey, alright, Flurky McCurky here. The last video on my Anatomy Assist playlist, this is the nervous system. Alright, skip the next minute if you just want to get to the nervous stuff, because I'm going to be talking about the paperwork stuff. Please like and subscribe to my channel if you enjoy what you see. If not, put a dislike and tell me why you don't like, and so that I can improve. Please comment something else you would want me to do. I do more than just teaching. I do entertainment of various items, and I'm more than willing to consider proposals. Just allow me the opportunity to consider them. I will not do anything that is crude or demeaning to another person. And I will do playthroughs of games, but only if they are games I feel comfortable playing and letting you guys watch. And letting my little siblings watch. All right, with all that out of the way, into the nervous system. All right, so the nervous system contains the brainstem, and nerves. This is the brain. This is the brainstem, this lovely little thing that attaches to your spinal cord. And these are all nerves. It's divided into the central and peripheral nervous systems. Central being brain and brainstem, and spinal cord, and the peripheral nervous system being everything, just about everything else. Your brain is mostly responsible for all of the things that make you, this lovely massive purple flesh that is really, 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 really complex. Like all of this, see this? This is all computer. Like every single cell in this mass is another bit of computer. Speaking of those cells, they are called neurons. This is a neuron. I've zoomed in a lot here so I can show you all the cool little stuff. So this is a standard multilateral neuron. This is it's got dendrites, soma, nucleus, an axon. This one's myelinated, ending in an axon terminal with axon buttons, axon terminal buttons. To remember the names, axon, axle helps me because it's a line. Meh. Myelin, for movement. Remember, mya is muscle or movement, and myelin helps you move better. Remember, myelin is basically insulation to make your nerve impulses move faster. Axon terminal, it's at the end. Buttons, because there's a little button. Soma means body. This is a cell body. And dendrites. Remember, the Greek word for tree is dendra, and these are branchy. So they're dendrites. They look like trees. I have some notes here that I'm going to show to you guys in case you're pressed for time. And so remember, a neuron isn't the only cells we have to worry about on this test. We also have to worry about the neuroglia, which support it. But first, we're going to talk about how a neuron works. So in essence, it's a whole bunch of tiny switches. On the cell membrane, there's a whole bunch of switches that, when activated, they let sodium in, which changes the charge. It's called an action potential. I'm going to look that up now. So one moment while I reorganize this. So an action potential on a graph looks like this. This is measured in millivolts. So neutral is negative 70 millivolts when there's nothing happening. when a neuron is stimulated, these dendrites are detecting something, whether it's an impulse from another neuron or something weird happening in the body that it's specialized for, like I'll get to that. Then it activates sodium channels, which let sodium in, and if there's enough of it, then it depolarizes and activates the next section. So it looks like here's this giant miasma of cell membrane, and it's covered in switches. This one turns on, lets in a whole bunch of sodium, and it turns on, and there's this wave, and this wave travels down the axon and to the axon terminal, to the synapse. Or if these dendrites are touching other dendrites, then just straight there onto the next cells. After that, it reaches this area where because it's so positive, the potassium gates activate, letting the positive out until it goes all the way back past regular, and then it goes back to homeostasis to do the resting state again. And this whole thing can happen in 15 milliseconds. This whole thing, like from here all the way to when it's ready to fire again, happens in 15 milliseconds. So that's pretty darn fast, or at least in each segment. So yeah, every 15 milliseconds, a neuron can start another level of stimulus. So yeah, there are 3 different kinds of neurons. There are the sensory neurons, the ones that detect the environment and when the dendrites are exposed to a particular stimulus, whether they be chemical like in your olfactory nerves, or pressure, or golden heat like on your skin. They are triggered and send the signal down the axon to a number of interneurons goes straight from here where it's detecting and up to here to spinal cord and to the brain where you process it and think deeply about the stimulus you have just received, or not so deeply, like ow. Oh. So yeah, and there are motor neurons which go from the brain and spinal cord to straight to your muscles or glands. A motor neuron will always activate a muscle or a gland. And on a muscle, it'll make it change shape. On a gland, it'll make it release something. So on my salivary glands are working very hard to keep up with my mouth. I have nerves going from my brain to my salivary glands, and making them squish and release their saliva. And those are motor neurons. Sensory neurons are for my skin. They're telling me I'm slapping myself. And interneurons are the third type of... Did I already say third? The third... so there are sensory neurons, motor neurons, and interneurons. Interneurons go between neurons. You can have a whole bunch of interneurons talking to one another, making a long, complex think about process. Or you can have like one interneuron, which goes from one sensory neuron to one motor neuron. Things that are that short are called reflexes. And there are 4 different kinds of reflexes. There are cranial, the kind that goes to your brain, you think about it, and then goes back to motor neuron. The kind that sensory neuron, there's spinal, where it goes from sensory neuron to your spine, like 1 or 2, maybe 3 interneurons, and then you react really fast. And that's the spinal reflex. The cranial reflexes, you think a little bit about them, but you're not really thinking about it. It's just like an emotional thing often. And then there's also somatic. Yeah, there's somatic reflexes, which are kind of weird. They're the ones that help you stabilize while walking, mostly controlled by your cerebellum. Back here, this little bit in your brain is called the cerebellum. It's also your tiny brain. It deals mostly with motor control and balance, and that's what somatic reflexes do. So, when it goes to cranial, it's usually speaking about your cerebellum, your either your cerebellum or your cerebrum. Somatic deal only with the body and tiny little things that help you stabilize while walking. And then there's the last kind, autonomic, which is like almost no interneurons. Certainly nothing spinal or cranial, because autonomic tends to do with digestion, and you don't want to have your spine or brain thinking about, all right, move this muscle to digest. I mean, maybe a little bit at the beginning for eating and a little bit at the end for, control of when you're going. But other than that, I mean, moving through your guts is really automatic. So autonomic reflexes are digestion reflexes. So the 4 reflexes are cranial, spinal, somatic, and autonomic. All right. So yeah, I think that's almost it. Oh yeah, neuroglia. So this is a diagram of some neuroglia. So we're going to list them first and then discuss them. So this is an oligodendrocyte. This is a neuron, so it's not a neuroglia, this is a neuron. This is a microglial cell. This is an astrocyte. And these are ependymal cells. Astrocytes, star cells, star site cell. Astrocytes give structure and rigidity to your brain, make it so that it's not this syrup all the way through. It's actually got some structure. That's the astrocyte's job. They also maintain the blood-brain barrier. They keep your blood a lot more sealed than it is elsewhere in your body. See, in these vessels, it's all closed up, whereas if you remember in our cardiovascular unit, it's a little bit more spacey when it comes to the capillaries, but your cranial capillaries are really sealed up, letting only oxygen through and only things that these cells have gates for. So things specific, very specific for your brain, like hormones or nutrients, glucose, lots and lots of glucose, and nothing else. So this blood-brain barrier makes it so that pathogens, viruses, not even the tiny viruses, can make it through. There is one kind of pathogen that can make it through the blood-brain barrier, and they're called proteinaceous infections, or proteins. They're really scary because they're only one protein. And if they make it through the blood-brain barrier, that means that they're identical to a protein that's naturally in your body. But there's this one protein called mad cow disease, which it's got all the same amino acids and chemicals and stuff as a PCP24 in your brain. It's a protein that helps you regulate your cerebrospinal fluid. But when it's the right shape, it's doing its right job. But when it's this particular shape, that's this protein, it doesn't work for its normal job. But what it can do is when it touches the normal shape, it changes it to that shape. So it becomes a game of sharks and minnows in your brain. You just kind of go catatonic. And you eventually stop breathing and die. So yeah, they take mad cow disease really seriously. For some reason. I don't know, maybe it's terrifying. I think it is. Anyway, so yeah, that's how solid your blood-brain barrier is. Nothing but things that are supposed to go through. And the reason pro-Atins work to get through is because they trick your brain into thinking that it is by getting through that one gate. Astrocytes keep the blood-brain barrier. They provide supports. Microglials are also known as cerebral macrophages. They are basically immune. They clean up debris from neurons and dead neuroglia. They generally make sure your blood-brain barrier is intact, and they make certain that your cerebrospinal fluid, the gel that keeps your brain up, is mostly the same. They're the custodians, if you were. Another thing astrocytes do, I almost forgot to mention, is that they have a small role in guiding neurons into different shapes so that to simulate learning. Oligodendrocytes, these cells that are putting what they do is in the brain, they put myelin on in the brain, they put myelin on neurons to make it work. And ependymal cells create, measure, and regulate and move around cerebrospinal fluid, the gel that keeps your brain up. They move it with all these microvilli and cilia, and especially with the microvilli, they make sure that it's what it's supposed to be so that your brain works. Pretty important. Another kind of microglia is Schwann cells. So Schwann cells are to your body as oligodendrocytes are to your brain. Schwann cells make the myelin sheaths in your peripheral nervous system. So basically up here and a little bit down here are oligodendrocytes, and everywhere else it's myelinated when it's myelinated by Schwann cells. So when nervous tissue is not myelinated, it's a little darker because myelin is really white, and it's called gray matter. When it's myelinated, it's called white matter. So gray matter, white matter. What other kind of neuroglia are there? There are, satellite cells. So, nope, not that one. That's not the tab I wanted. So, I will be back. One moment. So these are satellite cells. So on some of your peripheral nervous system, on most of your peripheral nervous system, the nerves don't look like this. On a lot of them, the soma here is to the side like this, and the axon just kind of goes through, and the soma is just there for life support for the neuron. Satellite cells myelinate and protect cells like this. It's called a ganglion, where this body's on this side. Schwann cells around the myelinating the axon. Satellite cells protecting the ganglia. So when it's on the side, it's called a unipolar. When it's up on one end like this, it's called a multipolar because you see the axon can go as many different ways as one. And when the cell body is in the middle and it's just one side, it's called bipolar. And that's not to be confused with the mental disorder. It just means there's two different ways the axons go. All right. So yeah, I think that's all the neuroglia. So now let's talk about the major nerves. All right. So in your craniofacial, so the major nerves are brachial nerve for left and right, and locomotor nerves for left and right. Your legs, and then your spinal cord. But also for the test for Lincoln High students, sorry if you don't apply here, we need to know the craniofacial nerves. So going over to anatomy, we're at craniofacial nerves. I'm going to turn off all of the other nerves just for a little bit. But first, all right, one moment, I will return. All right, so we need to know some of the craniofacial nerves. We need to know that this, no, turning on the pan so that I can just go side to side. See this one that goes like right up against the brain, right here. See that? This one? And then it has all of these droopy things down. That's called your olfactory bulb and your olfactory nerves. Then you have optic nerve, which goes right here. Right here. See this nerve? This is called your optic nerve. See, it's all highlighted. You have two of them, obviously, one for each eye. You also have two olfactory bulbs, one for each nostril. You're also supposed to know the oculomotor nerve, helps you move your eye, which also the trochlear helps you also move your eye. Then you have the trigeminal nerves, which goes to three places: your mandible, your ophthalmic, which more eyebrow and eye stuff, and your maxillary, which is up here. So maxillary, mandible, and just up here is your trigeminal. And then you also have your abducens nerve, which does more face moving. And your facial nerve, which again, more facial moving. Vestibular cochlear nerve, which helps you with balance because it goes to those cochlea in your ears, where all the fluid's swishing around and to tell your body what position your brain is. Your vestibular cochlear nerve, right over here, helps you with that because they're right there and they do that. And we also, for the test, need to know the glossopharyngeal nerve, which, helps you swallow and control, and a little bit of the tongue control. And then your hypoglossal is mostly just tongue control because it's, under your tongue, hypoglossal. And glossopharyngeal is, tongue, pharynx, throat. And then we also need to know the vagus nerve, which I will find eventually. Where is it that I may highlight it? Oh, great. All right, one moment. All right, I found it. It was part of, in here, it's part of the thorax, which makes sense because your vagus nerve, no, not that, your vagus nerve, you have two of them. They help you with control, with a parasympathetic control of your heart, brain, not heart and brain, heart, lungs, and stomach. Parasympathetic is fight or flight / rest and relaxation, where you control your heart rate, your breathing, so that you can be ready to fight or flight when you need to. It's also, and then we also need to know the accessory nerve, which I don't know what that is. I will be back. And the last one I haven't covered on this list that I couldn't find on the biodigital is called the accessory nerve, and it helps you control your sternocleidomastoid and trapezius muscles, so you can move your head and neck. They also have a particular list, See, this one's cranial nerve 11. Anatomically speaking, the Cranial nerve 1 is olfactory. Nerve 2 is optic. 3 is oculomotor. 4 is trochlear. 5 is trigeminal. 6, this is sign language for 6, is abducens. 7, sign language for 7, is facial. 8, sign language for 8, is vestibulocochlear. 9 is glossopharyngeal. And then 10 is your vagus. And 11 is your accessory. And 12 is your hypoglossal. So I'm going to make a list real quick so that you can see that. All right, here's a list. These are 1 through 12. In anatomy, professional anatomy, you would refer to them in Roman numerals, but I was having trouble with that. So 1 is olfactory, 2 is optic. It's right here. Remember, the trigeminal is split into 3 major parts: the ophthalmic, maxillary, and mandibular. And yeah, that's the. Is there anything else that I have? If there is anything else that I haven't covered, thank you, Mr. Wardlaw, our teacher, who reminded me that there is. I also need to go over some basic neurotransmitters, and thinking of it. Come to think of it, I haven't gone over the synapse, so I'll be right back with the diagram. All right, so remember those axon terminal buttons? The SDs. Inside of them are these little bundles of cell skin, cell layer, with called vestibules, right? Filled with chemicals called neurotransmitters. Transmit nerve transmitters. They transmit messages across neurons. So it goes from here, and it activates some sodium gates here. If enough of them activate, they starts an action potential on the dendrites. These are the dendrites of the receiving postsynaptic neuron. The presynaptic neuron here, see, sending neuron. This is the synapse, and then receiving neuron, postsynaptic, presynaptic. As the action potential goes down this length, it comes here and pushes one of these or a couple of these out, which goes to which lands on a receptor, letting sodium in and perhaps starting a wave of action potential. After the neurotransmitter has done its job, it's taken care of by an enzyme or sucked back up in reuptake, a process called reuptake, which takes back up the neurotransmitter. So this is an excitatory activation, and an inhibitory activation is if instead of activating a sodium gate, if it activated a chlorine gate, which is inhibitory, makes it even. So you remember the action potential, how at resting it's at negative 70 millivolts. Well, if you open chlorine gates, it goes even further, which makes it even harder for it to activate. So sodium gates make it activate, and chlorine gates make it not activate, like really don't activate. So in some cases, the same neurotransmitter will make it harder for a neuron to activate and fire, which is good in some cases, like say we want to not feel pain for a little bit. We have certain chemicals called endorphins that help with that by opening chlorine gates instead of sodium gates. All right, I'm really pressed for time, but some major neurotransmitters are for motor control, acetylcholine. For pleasure, dopamine. It does excitatory or inhibitory. For mood, excitatory or inhibitory, serotonin, and norepinephrine for no pain. It's inhibitory. Acetylcholine is excitatory for motors, but inhibitory elsewhere. Thanks for watching, and never stop learning. Bye-bye.